Inverse functions. I would like to recall first, if a function f is such that f of x1 does not equal f of x2, where x1 does not equal x2, then the function is called a one-to-one function. If a function is one-to-one, it is possible to reverse the assignment so the range will be assigned to the domain. Here's an example. So the function f(x) is an assignment from the domain to the range. If this function is one-to-one, we can also have a function that will assign the range to the domain. This is the reverse assignment. So the domain of the reversed assignment is the range of the function f. And the range of the reversed assignment is the domain of the function f. Here is a chart of a function f that is not one-to-one. F of -2 is 4, f of 1 is 3, f of 2 is 0, and f of 5 is 4. So you can see here that f of -2 equals f of 5, which is 4, which means that if we will reverse the assignment, we will get an assignment that is not a function. Here is the reversed assignment. This one is not a function. Observe what happens to f of 4. F of 4 is assigned to two different elements in the range. This means that there is no inverse for the function f of x. Here is a chart of a one-to-one function f. Here, the reversed assignment, which is the inverse function of f denoted by f to the -1x, is what? Let's see. It's exactly the opposite. The range of the function f is the domain of the inverse function. The domain of f is the range of the inverse function. The function f assigned -2 to 4, so f of -2 is 4. Here we get that f of -1 of 4 is -2. F of 1 is 3, so f of -1 of 3 is 1. F of 2 is 0, so f of -1 of 0 is 2. F of 5 is -1, so the inverse of -1 is 5, or f to the -1 of -1 is 5. You can see that this is just reversing the arrows. The range of the function f is the domain of the inverse function of f. The domain of f is the range of the inverse function of f. Inverses comes in pairs. If this function is the inverse of f, then f is the inverse of its inverse. We say that f -1x and fx are inverses of each other. To test if a graph is a graph of a one-to-one function, we apply the horizontal line test. Don't forget also that this is in addition to the vertical line test. If any horizontal line intersects the graph at most once, then the graph is a graph of a one-to-one function. I recall this example. It is a function, but when we apply the horizontal line test, we figure out that this function is not one-to-one. This is a graph of a function, and this function is one-to-one. it is possible to restrict the domain of a function so it will be one-to-one. Example. We already know that this is a graph of a function which is not one-to-one. But if I will restrict the domain of this function only to this part, then it is one-to-one. Here's the horizontal line test. The restriction is not unique. Here is another restriction of the domain. Let's apply the horizontal line test. It is the graph of a one-to-one function. Example. f(x) equals x to the power of 2. Here's the graph of the function. We apply the horizontal line test. Definitely not a one-to-one function. We can also show this directly. f of 2 equals f of negative 2. So it cannot be a one-to-one function. It means that f(x) equals x to the power of 2 does not have an inverse. Which means that the function square root of x is not the inverse of x to the power of 2. To create the one-to-one function of f(x) equals x to the power of 2, we will restrict the domain to be only x greater or equals to 0. Now, this is a one-to-one function, and f(x), which is square root of x, is the inverse of the one-to-one function f(x) equals x to the power of 2, only when x is greater or equals to 0. It is true that the square root of x to the power of 2 equals the square root of x to the power of 2 only when x is greater or equals to 0. The graphs of a function and its inverse are symmetric with respect to the line y equals x. Example. This is a graph of a one-to-one function. We will use the symmetry with respect to the line y equals x to sketch the graph of the inverse function of f(x). It's this one. Here is another example. We know already that when x is greater or equals to 0, x to the power of 2 and square root of x are inverses of each other. And indeed, we can observe the graph of those two functions, and we can see that they are symmetric with respect to the line y equals x. Here is a way to check algebraically if two functions are inverses of each other. So this is really a theorem. The one-to-one functions f and g are inverses of each other if, to any x in the domain of f, g of f of x equals x, and to any x in the domain of g, f of g of x equals x. We are now going to do this example, and we are going to check that those two functions f and g are inverses of each other without sketching the graph. All we need to do is to do two compositions, f of g of x and g of f of x. We will start with this one, f of g of x. It's 2 times the function g of x plus 5. We simplify the algebra and we get x. Now to the other composition. G of f of x is g of 2x minus 5. We will replace the x in g of x by 2x minus 5, simplify the algebra, and we get x. Only now, because of the theorem above, we can conclude that f and g are inverses of each other.